fact, I just bumped into somebody in the hallway earlier, and we ended up talking about it, and he had a very different perspective on the whole talk than I did. That just happens because we had a collective experience, and we're walking around.
Hi, good afternoon, everyone. I'm Roy, and today we're going to talk a little bit about ranges. I'm very excited to be here, to see you all, and let's get started. As I mentioned, my name is Roy. It's actually pronounced Roi in Hebrew. I live in Tel Aviv. I've been doing C++ for quite a while now, and in the last 11 years, I've been working for Easter Research, a low-latency trading company out of Israel. I'm always happy to be in these types of forums to engage and talk with people. I really encourage you to ask me questions as well. Let's make this interactive. The QR code, by the way, is for the slides, and I also posted the link on Discord if you like. Today, as I mentioned, we'll talk about ranges. We'll actually start by talking more generally about libraries and template libraries in C++, try to understand what they are, and then we'll dive a little into the ranges library, understand what's good, and maybe what the strengths of that library are. And then we'll go looking for rabbits. Libraries. If I try to do like an association game, what comes to mind when you hear the word libraries or library for software? So when I think about it, one of the first things that I think about is code that's for coders and not for like users or other people. Or sometimes I think of it as like something that's self-contained and reusable, a piece of software that I can go and give to someone else and can be used as its own thing. Or maybe an abstraction layer, something that has a very distinct inside and outside, and where people can rely on what's going on inside without really knowing the details. Sometimes when people think about libraries, they even go as far as thinking it's like a language within a language, like with its own vocabulary. It can sometimes be called like a domain-specific language. And another way to think of libraries is like as building blocks, as these like puzzle pieces that you can hook up together without, again, knowing too much about what's going on inside. Another thing that people always talk about when the libraries come up is the notion of the API, the interface. And the interface is ideally a very, very, very simple, even if the implementation is tricky. And if we use libraries correctly, then they enrich our language. They give us more words to speak with each other about. So libraries don't only let us communicate and write better software on its own, but it also gives us a way to communicate with each other. And I'm sure there are other definitions and associations that come to mind when you think about libraries. And let's see a little clip from long, long ago from 1984 from Hal Abelson, who's one of the authors of this book called SICP, Structured and Interpretation of Computer Languages. And let's see what he has to say.
But the important thing is that between these and these, we set up an abstraction barrier. We set up a layer of abstraction and what was that layer of abstraction? That layer of abstraction was precisely the constructor and the selectors. This layer was make-rat and numer and denom. This methodology, another way to say what it's doing is that we are separating the way something is used, separating the use of data objects from the representation of data objects.
Okay, so separating the way an object are used and the way they're represented. Okay, so I don't know if you've heard of SICP, and I encourage you to get to the link and see this book, and there's a course based on it with really like a lot of the fundamentals of just writing large-scale software. And In here, again, there's a big emphasis on the fact that we write libraries in order to create those barriers, in order to make things more scalable. So we can write large systems without thinking of every little piece of detail that's across the abstraction layer that we've created for ourselves. And so we know what libraries are, and I want to try and advocate that we should write libraries. Libraries is not just something that professors write or library influencers in some ivory tower write. We should also think about libraries. And why is that? So first of all, libraries, they enable reuse. Okay, we know we don't want to repeat ourselves. Again, the notion of vocabulary, it can help us in day-to-day life. And many times in our workplaces, or wherever we write code, we need to converse with people many times on topics that are very, very specific to our own organization or to our own groups. So we need our own words many times. So developing these types of vocabulary is important, and writing libraries is a way to do it. And thinking of things in terms of building blocks also helps, because typically, if we have building blocks one on top of each other, the higher we go, like the top tiers, they're the ones that are most like customer-facing, and they usually change more rapidly. There's more change going on to them, so it's very hard to reason about and to try and predict what's going on with those blocks, or what will go on with those blocks, like 3 months from now or a year from now. If we go down a few layers, we can get to areas that are more stable, potentially more robust, potentially more testable. So if we go and break up our system into different layers, there's a better chance that those areas that are most complex will change less often. If they change less often, we can make them more stable, more robust. And again, thinking of these libraries as abstraction layers as we work will also help us, because again, whenever there's something complex, we can encapsulate it and not think about it too much when we don't have to. It's safer when these things are on the other side of that barrier, on the other side of that abstraction layer. So if we try to think about our code and understand what are the barriers and which barriers we really trust, that we can really only think of things as their interfaces and not know or reason about their exact implementation, will typically help us. And again, as the lower we go, typically things can be better defined. We can, on the low levels, it's usually easier to think about preconditions and postconditions, and to really reason about what exactly we expect the inputs of a library to be, and what we can sort of guarantee about our outputs, or the way that the library does. And again, the lower level is typically more testable. And another thing that I think people sometimes don't appreciate is that it's not just a two-layer model where there are libraries and application. Libraries are typically built on top of other libraries. It's like stacks. It's like libraries all the way down, or turtles all the way down. So that's the way to think about it. And so whenever you think about writing library code, you don't have to consider yourself just being on plain C++ ground or plain assembly. You can always compose different libraries together and create your own. And on that note, a few months ago, I went to the CPP Now conference, and there was a talk about safety by Sean Parent. And this is one of his slides from his talk, where he basically even describes a somewhat more extreme potential, where we have a large library of proven generic components, and the mix and match, or the composition of those components, is potentially not even Turing complete. So the ways to compose different library objects in a potential future that might be good is to have only those generic components and a very, very simple way to compose them. And I think this is an interesting concept as a way to try and create more stable, more safe code by making sure that the complexities only reside in those components that are generic and proven. So, okay, we know what libraries are. We want to write them ourselves. How would we go about it? So again, there are quite a few talks online and presentations and ways on how to go about it. So one tip that is commonly referred to is that typically you should start with the algorithms. Okay, start with these things that you want to get done. Okay, some piece of code or some logic that you need. Then you write your basic implementation, and then you go on this iterative process of generalizing, distilling, simplifying, okay? You try and make this very concrete use case that you have and try to understand what's at the root of it, what's at the core of it, and how can I make just a specific goal that I have into something that maybe is useful for someone else who's not exactly in my domain. And out of that generalization work typically is where objects or concepts will emerge, will come out. And that by understanding what are the actual attributes that we see in those pieces of information that we want to consume and those results that we want to generate. And another tip that often comes up is that a special attention needs to be given to the API. APIs should be easy to use and hard to misuse. And there's a whole piece of art, and there's a lot to be said about it, especially in C++, where we have obviously the notion of constructors, destructors, move-only types, a lot of things to do with like operator overloading. You can very easily make things very easy to use, but you can also potentially make things easy to misuse, so pay attention. And another thing that we should always think about as we design our APIs are what the preconditions and postconditions are. There is work for the C++ standard of adding contracts, which will be like a more formal way of describing what the preconditions and postconditions of our libraries going to be. But even before it's in the standard, we should keep that in mind. We should at the very least document it and sometimes maybe assert it in various cases. And another topic or point that comes up from time to time in talks is whenever you have an algorithm and it does anything that's non-trivial, try to give as much of the non-trivial information that you've calculated back to your caller, because you don't know what they might want to do with it, even if it looks like an intermediate result or something that's not specifically tied with what the algorithm aims to create. And the last tip that I hear from time to time and think you should also keep in mind is the use of regular and algebraic data types. When people will use your types, will use your code, they will want to think about what, or make analogies to things they already know about. People know about integers, they know about floating points, they know about the containers in the STL, and we should strive to make our types similar to that. So the notion of value semantics comes to play, and they typically behave well inside other library components in the language. And sometimes when we have these notions and objects, we might want to look at it mathematically and say, are these objects a group in some algebraic world? Or is that a monoid? Or are those monads? Once we understand or get the notion that a specific type of object that we want to use actually has some algebraic behavior, it can be very easy, much easier for us to get a grasp of how we want to implement it, whether we want to perform operator overloads on it, whether we want to make sure that its operations are associative, whether we want to clean it up. If it's almost a group, how can we make it a group? And that way we can make whatever components that we build more generic and easier for others to exploit and understand. So, okay, we know how to write libraries, and we want to go in and do it. But again, how do we go about writing new algorithms? That's the first step. And so the basic idea is that algorithms, they're everywhere. They're not just in CS textbooks. And there are many places where you can go and look and find ideas for things that potentially can solve your problem. And you can borrow ideas from those places. And you can also look at your old self or your team's old code base or existing code base and find those examples that can be distilled into library components. And again, I want to give you some blast from the past with a talk from 2002 from Alexander Stepanov. He's the main developer, the inventor of the STL, and he was also asked to talk about finding new algorithms and how did he decide to collect these things into the standard template library. So let's hear him out.
Unfortunately, in 20th century, there is a very wrong idea of science developed in popular culture. And Einstein, who was, of course, a great scientist, is partially responsible for that. The idea is that scientist is somebody who has long hair, never gets a haircut, seldom washes, and discovers some wonderful, wonderful things because of some inspiring breakthroughs. And science is actually, it's something you do on a regular basis. I think a much better paradigm for a scientist is somebody like Carl Linnaeus, who established modern zoology, which is you send your disciples all over the world to bring you examples of animals and other living species, and then you try methodically to classify them. Science is about classification. Science is not about grand inspirations.
Okay, so science is about classification. Science is not about great inspirations. Okay, so the basic methodology that Stepanov used, and you're obviously encouraged to go and watch this entire talk, and that I think we can all use, is by just looking around and trying to classify what we see, whether we see commonalities, and try to understand what of these commonalities we can, distill, improve, and in order to make things easier for next generations or for maybe the person next door. So we talked about libraries in general and how to write and find and add ones. Let's talk about ranges. So the ranges library, I think, is a breakthrough library in C++. It's one of the big 4 features on C++20. And it again, wasn't invented in a vacuum. It wasn't like a grand inspiration. It rests on decades of existing libraries and experience. Obviously, a lot of it has resemblance and communicates well with the C++98 iterator-based algorithms and model. And then there are a lot of fundamentals in functional languages and array languages, like APL, BQN, et cetera, and you can go and see Connor Hoekstro's talks about it. It also rests on similar libraries that exist in other languages, like the D language, the Rust language, the Java language, and there are various talks that compare between those libraries. So C++ ranges basically had the advantage of coming in a little late to the game. Okay, when C++ ranges were added to 20, there was a lot of preliminary work done in other places that ideas could have been borrowed from, which is, I think, great. And the main innovation from my perspective of the library is the notion of composability. Okay, and what's composability? So it starts with the fact that many of the algorithms in the ranges library, they just take ranges as input and return ranges as output. Okay, and if I take ranges as inputs and outputs, it's very easy for me to just put the output of one algorithm as the input of the other and just chain calls one to another. Compare that to C++98, where things were based on iterator-pairs, and there's no way to to pass the result of the resulting iterator pair of one algorithm into the other one very, very seamlessly. It was all much more complicated. And then there's the notion of range adapters, and the range adapters which encapsulate lazy ranges, sometimes called views as well. And those are components that perform algorithmic work in a more lazy fashion. And again, they were specifically built in a way that can be composed, that can be just added and chained one to another. And there was specific mechanisms, done in the ranges library to make it easier for us, and we'll see it later. Another, less, I guess, appreciated part of that is that when we create these chains of range adapters, we typically think of it as a chain that starts with some actual range, and then we pipe other operations on top of it to get a different range. But we can also create a chain that only contains those adapters and nothing more. And if I just create a chain of various adapters, then what I get in my hand is just a different algorithm. It's just the composition of others, and this is a different algorithm that I created. And sometimes this notion is called expression templates as well, like these ways where you can create and compose different expressions, I guess, and use them as a building block. Another addition to the library that adds to composability is the use of projections. Projections is a notion that was added to many of the algorithms in the ranges library to allow some unary transformations on the ranges that we inspect. And typically, it really makes it easier for us to make like minor tweaks that otherwise would have caused us or need to break our code apart, or even make unnecessary copies, or write some, let's say, inconvenient or inconvenient like lambda functions or whatever. So let's talk more about the composability of ranges. So again, this is a good example of just chaining things because the input types and the return types are the same. So I can take a string, I can search for the ABC substring in it. The return type is a range by itself. So I can go and pass that into reverse, and I get the reverse of whatever I found. So that's one example. And again, with views, which are like these lazy ranges, I can go even further and use this pipe operator. And again, so I can take a string, pass it to this adapter that splits it by a space, and then take the first two words. And again, this looks like a chain. You read it from left to right. And basically a way of composing various operations that I want to do on my range. And as I mentioned before, this pipe object doesn't need to start with a range. So let's see what this square evens, I guess, object is. So it's a pipe of two objects. It's a filter and a transform. Okay, so it filters anything that's even and transforms it by squares it. So what's the type of this thing? Okay, so and the answer is that we don't really care about the type, but this is a variable, an object, but it's also an algorithm. Okay, I can pass it along just as if it's an object. Okay, I can have functions that are templated on it or receive it as an argument, but it's a generic algorithm on its own. Once I have this square evens object, I can use it to square a range, like a vector of integers, or to square all the evens in a linked list of floating point numbers. I can do all of that with this object. It is you can think about it as an object, you can think about it as an algorithm. There's this duality that comes into play, and this duality allows us to, again, have things compose better. So here's the list of the views, or like the most of them, I guess, in the standard. The ones with an asterisk next to them are in CppCon. There are quite a few of them. I don't expect you to know them all by heart, but getting to know and getting to use them is I think, a nice exercise and something to think about. I tried to group them based on the ranks of the sequences that they work on. So let me talk a little bit about ranks. So ranks is sort of like dimensionality. Okay, so if I have a sequence of integers, then it's like a dimension 1 array, right? But I can have like a sequence of sequences of integers, and then we can think of that as something that's like a dimension of 2. Okay, and so a sequence of integers, one can consider it as sort of like a matrix or just like a list of lists and something like that. And basically we have some views that are just factories that typically will be at the beginning of a chain, like the single view that creates just a view with a single element, or a repeat that just repeats an element infinite times, for example. We have the rank preserving ones will typically, accept a range of a specific shape and will return a range of that same specific shape. Now, obviously, if I use transform to accept an int and return like a sequence of ints, then it won't retain its shape. But typically, those are used to retain the ranks. And then those are the most common views. Most commonly, we use sequences and we just make various manipulations, but don't change the ranks. But there are some cases where we do want to decrease or increase the ranks. And in C++, the ranks can come in the form of sequences of sequences, or in the form of sequences of tuples, because tuples, their dimension is known at compile time. So again, we have the elements, keys, and views. Algorithms that take a sequence of or a range of tuples and reduce it to just a range of elements. We have a join and join with that take sequences of sequences or ranges of ranges and tries to just flatten them, so to speak. And then we can also increase the ranges with things like zip, enumerate, split, slide, etc. So there are many views in the standard, and there are obviously a lot of more views in the pipeline for next version of the standard. There's actually a very good talk that was created before, or when C++23 was in early stages, with a big prioritization of many suggested adapters, with some priorities on how soon and how early we should go and add them or implement them. So again, I encourage you to go and look at that. It can be sometimes enlightening, or can give you some perspective on what are things that can be done, what things maybe exist in other languages, etc. So let's take a short digression and talk a little bit about this notion inside the ranges library that's called the algorithm selection. And the basic idea here is that sometimes the same goal can be achieved in several ways inside the ranges library. So for example, there's ranges : s size or sign size, and ranges : distance. And the description that I wrote there is from CppReference.com. So basically, the first returns the signed integer equal to the size of the range. And the second is the distance between the beginning and the end of the range. So those are actually very similar in nature, but still there's a difference. And I learned about it a lot on CppCon just a few months ago. And what's the difference? The difference is that signed size has to run at constant time. Okay, and the library tells you that whatever you can run s size on will succeed at the constant time, or it will not even compile. Whereas distance is sort of more generic. Okay, if the compiler knows how to calculate it at constant time, it will do it. If it doesn't, it won't. And there's actually like an opt-out semantic concept called the disable sized range, which is a matter for whoever implements containers or ranges to tell the compiler, hey, can this specific range or can this specific container know its size in constant time or not? And these types of selections and these types of ways of choosing between different approaches on running the same thing is prevalent. It happens in more places inside the ranges library. And the way that it's done is using concepts. Okay, so concepts is another of the C++ large features. And it's used to tell the compiler like how to choose based on different constraints which implementation to go with on different types of ranges, different types of inputs. So the compiler can know what's the best way to reach a goal without runtime overhead. And this notion of algorithm selection existed before concepts. There were many ways to do it. C++98 or STL98 famously used the tag dispatch. But the concepts are much more flexible. They're much stronger, so they allowed a larger variety of ways to do these types of manipulations and get the compiler to help us choose the right algorithm for right cases. And I took this digression because I think we'll later see cases where this algorithm selection thing can help us when we think about potential new algorithms or libraries that we want to write. So let's go on and talk about like potential problems, potential algorithms that I've found around me, and some ideas of where maybe the existing ranges library was a good step forward, but maybe can take another maybe small step in a good direction, and where I'll give you my perspective, and we'll be happy to see what you hear of that. So before doing that, let's take another movie break. And again, talking about this notion of classification and finding good, I guess, candidates.
I have to meet occasionally with people who are doing so-called research in computer science. They say, well, I don't know, I don't have any ideas. Don't have to have any ideas. Go catch rabbits. Go look at people's code. Find what they do and try to abstract it.
Okay, so Stepanov is asking us to go and catch rabbits. Okay, go look around the world and find some examples. So this is a good example that I found that really got me thinking about this entire talk last year in CppCon, where I caught Tina Ulrich with a great talk about ranges and about how to take non-range code and rangeify it. And this is one of the more complex examples that she gave about this algorithm called the Hondt method, which is used in democracies to assign seats to a parliament. So the basic idea is that I'm going to have an election, and there are various parties. Every party wants to fill the parliament with its own members, but eventually each party gets a different number of votes, so we need to choose how to fill the seats. And in this example, we have a parliament of 7 seats and 3 parties, and like party number 1 received 110 votes, party number 2 received 85 votes, party number 3 received 35 votes. And the Hondt method basically tells us that we can take this like table of each and every candidate on each and every party. So this is like the first candidate of party number 1, the second candidate, etc. And we can give each of them a score. And the score is basically the number of votes that the party received divided by their own position in the party's list. And once we get these scores, we can go ahead and sort the scores of all the different candidates, and we'll just assign seats to the candidates with the best scores. So the first seat will go to party number 1, the second seat will go to party number 2, the third seat will go to party number 1 again, the fourth seat to party number 2, then party number 1, party number 3, and lastly party number 2. Okay, so that's the basic algorithm. And Tina gave a good example and a good way of how to take this code and write it in a range-like fashion. Okay, but one of the things is that we can create this table, and a key part of the algorithm is to go and sort it. Okay, so we have basically in this case 21 cells, like 7 times 3, 21 scores, and we need to go and sort them. And sorting in the STL currently, even in the ranges library, is not a range adapter, it's not a view, it's an algorithm, it's an eager algorithm, because sorting is something that is very hard to do in a lazy fashion. And so this is, again, a few lines from Tina's talk, where she basically uses ranges sort with this array of 21, or range of 21 different cells, basically taking them based on, like, we want the ones with the highest score to come first. And then right after sorting, we go and cut and take only the top one. So we resize it and take only the first few elements. So that was what Tina presented, and it was really, really good. And only just a few days later, as I was on my way back home, I thought about this problem again. I thought, hey, this can be improved. And so here are a few thoughts that came to mind. I'm sure that some of you already thought of them as well. So first of all, as I mentioned, sort is an eager evaluation. So if you want to sort something, we need to store it in memory. In this case, we have P parties and a seat, so we need S times P cells of memory, and the sort operation will typically run in SP log SP amount of operations. And then there's the resize that happens, and the resize implies that we're sorting too much, right? We are sorting all the 21 elements, well, in fact, we only need the first 7, right? So happily, there's a way to do that. There's an algorithm for that instead of sort, which is nth element. And the nth element will actually, will be able to not only find, or partition the first 7 and everything else, it won't even bother with ordering those 7 among themselves. It will just give me the first 7 and the 7th one as well, which is basically what I want here. I don't really care, which are, what's the ordering among them. I just want to know who's in the parliament and who's out. Okay, there's also, by the way, partial sort if we do want the ordering within those first 7. And then the last thought that I had, which really, got me to thinking a lot about it, was the fact of merge, and the fact that we were looking at it as just one large range of 21 cells, but actually this is not one range. These are 3 columns. These are 3 columns, and every score in every column is already sorted. Okay, so if you want to sort 21 elements, that's the sort algorithm, but if you want to sort 3 ranges that are already sorted, there's a different way to do it. Okay, and that is called merge. Okay, and merge already exists in the standard in some fashion. And the interesting thing is that merge not only is a better way in terms of complexity and can get us down to S log P, it's also lazy. Okay, so and once we understand that merge is lazy, we don't need to allocate. We don't need to create a RAM. We can just generally, we can create like a lazy, like these lazy ranges, like start with like iotas, divide them or divide the number of votes by them, create like a range of ranges, and try to work our way and see if we can then basically pick the top of these first three. Once we pick the top, we just take it out of, take it into our result, and then take the next best one, et cetera, which is in essence a lazy type of operation. It has some differences from existing range views, but in general, it's not an eager operation, it's a lazy operation. It can be done in a one-by-one fashion, like sort of like an increment that we can do in an iterator. So that's our rabbit number one. Why not introduce range views for sorted ranges? Like, so there's merge, and there are also a few others that we can easily think about, like set union, set intersection, and set difference. Those all exist actually inside the STL algorithms, and they can be views just as well. And most of them can also benefit in terms of performance if you make them variadic as well, or supporting like multiple inputs, like again a range of ranges where we have an unknown number of ranges that we're working with. That's typically done with data structures such as the heap or priority queue, and that means that that algorithm will need to find some way to create a heap or priority queue somewhere. And right now, there are variations of this in C++, but not exactly this. So again, in-place merge includes all these algorithms here already exist in the STL. Their preconditions specify that they can only work on sorted ranges, okay? And they accept a range and a comparator. And if you try to give them something that is not sorted, then you're on the hook. The compiler will not help you. This is undefined behavior, what's called library UB, and the compiler won't help you. But they exist still. And potentially, we can do something similar with these new views that we create. We can put the onus on on whoever uses those range adapters to make sure that they only pass us things that are correctly merged by the correct comparators, or correctly sorted, excuse me. And then the STL also has some other operations that work on sorted ranges, which aren't exactly ones that accept a range and output a range, but are a little bit different. Think of upper bound and lower bound, right? Those do binary search, okay? And binary search is something that's very useful if you have something sorted. And one would think maybe there's reason, or maybe there's we can think of those things as something that range adapters can be useful for. Similarly, equal range, where again, if something is sorted, we can find just a block of items, consecutive items that are all equal to a specific element. And there's also a unique. Unique is an algorithm that's not specifically tailored only to sorted ranges, but it's very commonly used when the inputs are sorted, because the way that it works is just just collapses consecutive elements that are equal, just so they are unique, but it doesn't look ahead or doesn't do much more than that. So for that reason, it's typically used mostly with sorted ranges. And as I mentioned, all the operations in my first bullet, they seem lazy in nature. It seems like there is value, there is a way to do them in like a step-by-step fashion, so that they can, in a manner that really composes well with the rest of the ranges library. And actually, I was, after I thought about that, I started looking around, and I noticed that ranges v3, which is like the basic, work of art by Eric Niebler, that was sort of like the prototype for standardization. It actually had views for set union, difference, and intersection. It didn't have merge, which is the one that I wanted, but at least it had those. The only small caveat was that those views in ranges v3 only accept two ranges as two different arguments. it wasn't variadic, it didn't work with runtime ranges of ranges, but the basic notion is there. It means that, I'm not out of my mind sort of when I'm thinking that this is maybe potentially something that people can find useful. Then I looked a little further and I also saw that the D language actually has both merge and multi-way merge, or merges ranges in a variadic nature where it's known in compile time how many streams or ranges I want to merge, and multi-way knows that in runtime, and it also does a nice trick in order to avoid memory allocation. So looking around and starting from an idea, an algorithm that I had, and looking around like in other places to see where similar implementations exist, what has been done already, really helped me understand better what I might want to do, how these things can potentially be done, and try to distill these things into more concrete ideas and things that can be added very, very succinctly. So that was our first rabbit, and that's where I started talking with other people about it. And that gave rise to other ideas about the notion of sorted ranges and the fact that they are somewhat neglected or not thought about enough currently in this C++ standard. So more ideas came up. So equal range and unique. Again, they can also be views. They have the right signature. What do I mean? Both equal range and unique, they accept a range as an input and return a range as an output. So it's relatively easy to take and to make them potentially views. And I thought a lot about searching, like lower bound and upper bound. Is there a way or a reason or motivation to take binary search and make it into something pipeable, to make it into something that's part of a pipe? So I don't know, you probably, some of you might already have great ideas about that, maybe even better than what I'm going to show here. But what I figured is that we already have take and take while and drop while. We can also go and have take until and drop until, where I know that the range is sorted. I can do a log n search for a specific value and take or drop anything before or after it, which is a common operation that one would do. For drop until, it's obvious that you need the log n search, right? Because when you call the begin on that type of view, you want to run as quickly as possible to find that value and move the begin iterator to that place. With take until, it's a little less intuitive, because if you're going to take everything until the value, then you're going to walk on all the values one by one. It seems like there's no reason to do the log n search for the end iterator, right? But sometimes it makes sense to search for the end iterator, because if I have a view where I know both its start and its end, I preserve some properties, right? I know that if the range was random access, then it will be random access even after this take until operation. If it was bidirectional, it's also bidirectional, etc. Obviously, if the range that I'm trying to pass in as input is not random access, then this is all meaningless, right? If it's sorted but not random access, then I can't do the log n search, right? Log n search requires that. So we can go for the S size approach or for the distance approach. We can decide that we won't compile with something that's not random access. Or we can decide maybe that it makes sense for take until, for example, to compile but just not know the end iterator in advance and just go one by one and just lose all those properties of being sized or bidirectional, et cetera, et cetera. And then there's also take between, okay? And so many times, so I work in finance, and in finance, many times we work with the time series information, and many times it's very common that we want to zoom in on some section of the day. We want to zoom in on everything between like 9:30 and 9:35. So we want to take, the range is sorted, I want to take everything in that range. And if you think about it, taking everything until 9:30 and dropping everything, like I guess after 9:35, it's each of the operations is log n, but it's not the most ideal operation. Like if the time series is for the entire day, 9:30, 9:35 are pretty close by. A lot of the steps on the binary search are very, very similar between 930 and 935. If I do take between, it's sort of like the optimization of min-max, which is faster than min and max, you know? So it's also something that maybe people can appreciate. So we can have many, we have these ideas, these algorithms, and as we've seen in previous talks, out of these algorithms, maybe a concept can emerge. Yeah, we can suddenly think of maybe we not only want to write these and have these algorithms or views, maybe we want to also add a new concept to our library, which is a sorted range or something like that. And that concept of a sorted range is something that, in some sense, the compiler will know about, and maybe the concepts range will not let us run swaps on it or make any changes that might ruin the sortedness of it or make it UB. And this sorted range might also know to tell us what its comparator is. And again, make things easier for whoever writes things to not make mistakes. And we know that stud map and stud flat map are, in some sense, implementations of that concept, and they will not let any operation change the sortedness of them, and they also have this value comp member that can access the comparator. As I was looking for that, I also found that this exists in the D language as well. So the D language does have this type of concept. And the tricky thing here is how do we create something and know at compile time that it's sorted. So the D approach is nice. It basically had two adapters. One is called isSorted, the other is called assume sorted. And assume sorted basically just runs at constant time, just tacks on this sorted tag on a range. Basically, again, gives the responsibility to the user. And isSorted basically sort of like returns an optional. It checks whether the input range is sorted. If it is, it will return that same range tacked with the notion that it is sorted. Otherwise, it will return a null opt, and monadic functions could go on from there. So potentially, if there are enough use cases where this can come to be handy, where these algorithms are handy, and we want maybe the compiler to help us a little bit and to not make mistakes, we can also add this concept to the language. It's obviously not trivial, but we can think about it. And another thing is the notion of just vocabulary. Sometimes there are algorithms that are not as complex as merge or binary search, but are so common that it makes sense to just create new words for them. So for example, again, something that's common in my place of work is you want to create a histogram. You want to know how many times each value appears if the range is sorted. So I'll chunk the range by equals to get a range of ranges of all those equal items, and then I'll transform each of them to the item itself and this number of appearances. Okay? And again, I chose to use distance here. I could have chosen size, and we talked a little bit about that as well. And here I'm just adding a word of vocabulary. Anyone who would want to create a histogram could have done it without this, but if we're adding a new word to the language, potentially other people will use it. And again, here too, one might think at a later point in time, or maybe even right now, that there might be reasons to implement histogram even for non-sorted ranges by using some unordered map or something like that. And that's obviously something that people can consider. And again, one of the strengths of the ranges library is it does this type of algorithm selection. So again, it's not just writing new algorithms or adopting things from STL98 or from D or from other languages. It's also just creating our own vocabulary for things that we think make sense. So this is
Go catch rabbits.
Rabbit number 2. And only one last rabbit to talk about, which has to do with the whole notion of sort. Again, I was thinking more and more about it, and I figured that sort by itself, we think of it as sort of like an atomic operation or a building block, but actually there are cases where it can be broken apart. And this thought was basically came to me because I'm also a programmer in the R language, which is an array language that's used in research and in finance. And there, sorting is done a little differently. And the reason is because sort is an n-log n algorithm, but it's like a maximum of 2 n-log n operations. There are 2 things that go on inside sort. Each of them is n-log n. What are they? So first, there are the comparisons, okay, and projections if we have projections. We run n-log n comparisons inside in the sort algorithm. And the second thing is the swaps, okay? We run n-log n swaps. And both of them, they can be expensive or they can be cheap. And the observation is that sometimes the swap is the dominant part, okay? So I'll try to give a few examples. The first example that I had in mind was, again, related to data series, okay? With the data series, we have these basically tables with many, many rows and columns, and I want to sort the table by one of the columns, okay? So I want to sort the table, for example, by the, I don't know, by the dollar amount of each transaction. So the comparison is just a comparison of dollar amounts. It's just a comparison of 2 integer values. But the swap might need to swap the entire row, might need to do a full copy of entire rows. So a swap is more expensive. And potentially, again, obviously you could have mechanisms where swap is just a couple of moves. So if the move is cheap, then things can work nicely. But again, there are use cases where a swap is expensive. And what's the best way to sort if I know that the swap is much more expensive than comparison? Can I do better than n-log n on both of them? And the answer is that sometimes you can. Yeah, so I talked a little bit about that. And the basic idea is that potentially, once you can try to do all those comparisons to figure out where each and every item needs to fall in, and only then do a single swap of every item to put it in its own place. Yeah, and the nature of projections, by the way, it's sort of like exacerbates, I guess, this entire thing. Because with projections, we basically are conceding to the fact that many times the objects that we are sorting, we're only sorting them by just a single portion or a single attribute of them. So here's the suggested algorithm, and the name order comes from the language R. In order, the order algorithm takes an unsorted range and generates the sorting permutation. Okay, so the sorting permutation is something that needs to be allocated somehow, maybe with ranges : 2 or something like that. And that permutation is typically, its size is linear. So you need to generate it. We can typically reserve it in advance. We know in advance how much to allocate. And this takes n-log n comparisons and no swaps. Once I've ordered things, I can go and do the swaps. I can apply the permutation with O(n) swaps, right? So it needs some memory allocation, but potentially it can lead to performance improvements. And the implementation of order can, if you want to try to hack it quickly, it can be very simple. It can be very easy. We can do it with IOTA and projections in some way, right? We can try to basically create an IOTA range and then sort the IOTA range based on a projection that looks into our input range, and that sort of thing. So that's a typical way to implement it if you want to do it very, very quickly and like off the cuff. So this is nice. This is potentially like an addition. Anyone who wants to use sort can use sort. If someone wants to use order, they can use order, right? Then I got to thinking more about this notion of permutation. Is there a concept behind the scenes? So what do I do with a permutation? So the main thing that if I have a permutation is to apply it, right? To do those iter swaps. I can also reverse the permutation. And by reversing the permutation, I mean undoing it, right? So if I apply the permutation and sorted everything, I can reverse the permutation to undo it and get back to the original state. And this is also something that's pretty typical in the line of work that I do. We want to maybe sort something, look at it in this way, and make sure to get it back to its original nature. And this application algorithm that applies the permutation is also, by the way, something that is an algorithm, but it can also be a range adapter or a view. It's also something that can be done step by step. It's a lazy thing. and then no swaps are required. I can create this permutation, access the data through that permutation, suffer all the cache misses or whatever, but not touch the data if the swaps are too expensive. So that's another thing that can be nicely done if we have this notion of permutation. I can use an apply permutation view on a range to apply the permutation and look at it in this reordered fashion. And actually, this also is nothing new. Once I got the idea, I started looking, thank you, and this exists in Boost, and this exists in NVIDIA's Thrust library. So there's already a notion of this permutation iterator, which is like a lazy iterator that works. Those were written for the C++98 world. I didn't really know about them because I'm a fan of the standard, and these are less standard, but they exist. And the standard library itself also has algorithms that deal with permutation. I don't know if you know of next permutation and last permutation, etc. And potentially, again, there might be room for a concept like permutation or permutation of some range. And again, we can maybe, like with shorter, we can well, once a permutation is generated, we know it's basically, what is it? It's typically a range of integers, right? Because permutations are just, positional indexes into some other range. But we have like semantic requirements that typically, if it's a permutation, then all the numbers from 0 to n-1 should appear there, and each of them should appear once, et cetera, et cetera. So these semantic guarantees need to be adhered to. And if I have this permutation concept, I can perform swaps, but maybe I cannot do assignments, et cetera, et cetera.
So just go catch rabbits.
So that's my third rabbit for today. And I really encourage you to also look around, try to find interesting ideas, try to look at the problems around you with the perspective of, is there something general here? Is there something that can be done a little better? If I look at a building block, can I divide it into other building blocks that make sense on their own? And maybe from that, concepts can arise, ideas can arise. It might make our code, our vocabulary more rich, more readable, maybe a little less bug prone. So libraries can make our software better, safer, and cleaner, hopefully. The ranges library is awesome. It's an exemplar of composability. If you don't know it and haven't tried using it, go ahead and use it. It's really a paradigm change in those specific fields or areas where you need to process sequences of elements. Potential libraries, as I mentioned, are all around us. And we can contribute, we can work on them. Even C++ ranges can potentially be enhanced. So go catch rabbits. Thank you very much.